Good evening to everyone. We are going to start our keynote session, and our keynote speaker is Dr. Zq Liu. He is currently a distinguished professor of material science and engineering at Pennsylvania State University, USA. He has been appointed to the inaugural Dorothy Page Enright Professor. He is also the director of Page's Research Lab. Professor Liu's research interest focuses on modeling and design of materials chemistry, and processing through integrating first principles calculations, statistic mechanics, thermodynamics, and kinetic modeling, and critically designed experiments for structural and functional applications. He has published hundreds of papers in peer-reviewed journals, and also he has recently published books on computational thermodynamics. Professor Liu is the immediate past president of ASM International, serving as the president from 2019 to 2020, and also he was the previous year he was also the vice president. And also he has completed his 3-year term on the Society's Board of Trustees. He was also a member of the Board of Directors with the TMS Society for 2008 to 2011, and the Board of Trustees of ASM International for 2013 to 16. Professor Liu received the Gibbs Space Equilibrium Award from ASM International, Hume Rodari Award from TMS, Space Equilibrium Award from the American Ceramic Society, and also Li Sun Lecture Award from the Chinese Academy of Sciences Institute of Metal Research. He's also founded the NSF Center for Computational Materials Design and coined the term Materials Genome, which focuses on the important building blocks of engineering materials. So I'd like to welcome Professor Liu for his presentation. Thank you. Please welcome Professor Liu.
Thank you very much. Thank you for the invitation to give the keynote speech here. And as the dean just mentioned, the pandemic is challenging. It's a challenge. At the same time, it gives us opportunities. Otherwise, I will not be able to speak to all of you today. So that's the other side of the coin, right? We should always remember that life is tough, but there's some other side of the life which is enjoyable, like this one. All right, so I'm going to share my screen. And there's my slides here. Great. All right, so as Professor Rashid mentioned, my talk is on the Materials 4.0. I'm sure that many of you have heard Industry 4.0. I want to see that the connection we're going to make with materials. My name is Zq Liu. My group website is www.basis.psu.edu. And I also have a YouTube channel. In case you're going on YouTube, you can watch a couple of YouTubes I put in there, not only about my work, but also about some of our projects there too. Okay, so let's start by an article I wrote together with Professor Susan Sinat, my department head at Penn State. Last year, The Bridge is the publication of the National Academy of Engineering in the United States. They celebrate the 50th anniversary of the issue of this magazine. And the question they asked was that, what's going to happen next 50 years? So as you can see that Professor Sinod and I wrote an article about the predicted advances in the design of new materials. So when we talk about materials, of course, we have to look at the past, right? So we talk about materials and civilization or civilizations. And you know that as you all learned, human used materials. And but many years ago, people used the natural materials like Stone Age. That's like a million years ago, until about the 2000 BC. And when people use these raw materials for nature, they found that they can do better. So they developed the Bronze Age. Now it's human-made material. Actually, the copper 12% of per weight percent of tin alloy called bronze. Then, of course, you can ask yourself, because I understand that most of you are either a senior or junior in college. So you know why 12%, right? Of course, you can look at copper tin phase diagram. You can see that 12% is a very unique number. If you have too much tin, what's going to happen? You have too low tin, what's going to happen? Okay, I leave that question to you. Hope you can go back to check the copper tin phase diagram. And after that, there's some problem. Challenge is that bronze is not hard enough. Okay, then people discovered, wow, we can do make some harder material. And so that was iron age started. Again, it's a human-made material. It's iron carbon alloys, basically. So because of the iron or the steels, and now we can do more things with it. So that's what it is. You can think about this one as a base of our industry 1.0. That's a steam engine, steam power. Steam engine is made of steel, right? So you need steel in able to sustain high temperature. And then gradually, when you get steam power, then so they can make it more efficient, right? So now you get electricity. Okay. When you get electricity, then people think, oh, gee, maybe we can do more things with electricity. Then you get computers. So this is basically talk about industrial 1.0 to 2.0 and 3.0. And if you think about the industry, this is 1.0 to 3.0, you really have to mix materials, right? Okay, so that's why it's connected to manufacturing. And when you do manufacturing, you have to pick up what kind of materials to make, right? You have to change chemistry. So that's what I put here. I say industrial, manufacturing, and materials, they go together. Without materials, you cannot make them. Without a manufacturing, you cannot do the industry revolution. Yeah, so it's all connected together. Of course, now we talk about Industry 4.0, right? So what is really the Industry 4.0? Of course, I'm sure that you read a lot of articles on that. But one of the important things is that it's called digitization, okay? So in Industry 4.0, if you really use one word to describe it, as you will see later, I like to use one word to describe things because that makes it more concentrated, right? So you don't have to kind of so diverse the meaning. But it's about digitization. So what is digitization? Numbers, right? It's numbers, okay? So Industry 4.0 is basically integration of cyber physical systems through digitization. So it digitizes everything. So when you talk about material manufacturing 4.0, it's basically you need the digital information from all steps from the beginning, when you dig the dirt from the ground, and the process into material, then the manufacturing into the shape, and get the properties you want, right? So you want to digitize all information you have from this beginning state. That's manufacturing. And then you want to do this digitization, you have to get the materials in place, right? You have to get the property of the materials when the material is in the dirt, right? So what the property is zero. Then you want to change the property of that mineral into some material. You have to understand both of them and the process, right? The kinetics. And then you want to make the heat treatment, the processing, the shape. Then you have to understand how that material behave at different temperature and pressure. Okay. So to do that one, as you probably know that in the United States, there were a couple of important terms we use. One is called the Material Genome Initiative. That was an initiative in the United States in 2011. And the Integrated Computational Materials Engineering, ICME, that was in 2008. If you Google online, you can get the reports on both. And when I was the president of ASM International, I wrote my monthly column on my kind of personal desk. In one of them, as you see the link here, I wrote one called Materials 4.0 and the Materials Genome Initiative. It's really put this concept together, say how materials, how important materials to support the manufacturing 4.0 and the industry 4.0. Okay, Talk about digitization. It's really knowledge, right? We basically digitize all the knowledge. So what knowledge do we have? Usually you see, you understand something, right? You have this concept, you connect the dots together, you build up the knowledge. Okay. So how do we digitize all of it? So talk about the manufacturing. So as I mentioned, it's changing materials from one product, for example, mineral to pure metal, and then you alloy them, right? So you add something you want into it, okay, to serve some functions or multiple functions. So during the process, you change of the materials, it's really change the phase stability. You say, okay, I want to change my condition so the minerals is less stable than the pure metal. Okay, so I make that process, I change the phase stability from one phase to another phase. Okay. So then you do the heat treatment, you do the liquid and casting, ingots, and do the forming. Everything's a big change in phase stability. Okay. So sometimes you want to control it, you want to change, sometimes you do not want to change. So you need to be able to control them. So by changing the chemistry, you can control which phases you want, that give you the properties you need. Okay. That's basically the manufacturing process. Now that means we talk about the phase stability. Okay. If you talk about phase stability, and of course you have learned the thermodynamics, right? That's in the 1870s, the thermodynamics, the foundation of thermodynamics or modern thermodynamics was laid by Gibbs in 1870s. He published a few books, a few papers at that time. 100 years later, the thermodynamics were digitized by Larry Kaufman. He created a field called CAFAT, calculation phase type. So from 1970s to 2020 to 2020, that's last year, 50 years, that's where the CAFAT-based material design become a practice, okay, because of the digitization of the thermodynamics. That's 50 years, right? That's what we wrote, that's the magazine, Bridge, 50 years, that's 2020. So now we'll talk about next 50 years, that'd be 2070, right? So when it digitizes more knowledge, like it digitizes more knowledge, in addition to thermodynamics, they think about after thermodynamics, what would be kinetics, right? After kinetics, you could have mechanical properties or any properties you have, right? So I put all the properties together, okay? So thermodynamics actually has a lot more properties than we typically think. Many people think about thermodynamics is equilibrium, right? But it's not. It's more, way beyond that. That's what I'll give you a few slides to demonstrate that, okay? One of my favorite topic in thermodynamics is entropy. I know that you have learned entropy in your thermodynamics class, but maybe you have not realized that entropy is a multi-scale. It goes from quantum scale, electron scale, all the way to universe. But I use this chart. This figure is animations from PowerPoint presentation. And so it's very very illustrative here. You see that you can see very small scale, right? And this is large scale. You can see this as a galaxy, right? Think about this as the planets, the stars. Okay. So what happens is that does happen. You look at literature. That's how people do. Okay. For example, if you have read this book by Stephen Hawking, talk about the brief answers to big questions. He talked about entropy and information of black hole. Black hole is huge, right? Okay. And if you read, I'm sure another book, it got The Order of Time. That's a newer book. It talks about entropy. Entropy drives the world. Well, entropy drives everything, basically, right? And he also made a very interesting remark that time slows down when moving faster. We know that they was saying that if you move as fast as the light, you'll be living forever, right? Okay. All right. So entropy is part of thermodynamics. We know that. Okay. But I do want to point out that to convince you, thermodynamics is so important, right? Because not only Einstein said, but he did say that the law of thermodynamics is the only physical theory of universal content. And we never be overthrown. That's because the thermodynamics is very simple. It's very simple when you start. But when you do the multi-scale, it's very complex. So it's the simplicity out of the complexity. Okay, that's the beauty of the thermodynamics. And I know that you are very young. You're still in your 20s, but some of you professors are probably older than my age. And I do want to show a very interesting book called Baby Loves Thermodynamics. Okay, it's interesting is that you probably know kids produce entropy, right? They make everything a mess. That's entropy. Okay, so they're natural. The natural process is to produce entropy. So if you get some spare time, maybe you can read this book. Particularly when you get married, have kids, and so you will not be upset if kids make a mess in your house, in your home, right? That's because if you do that, you will see that's great, because that means your kids, they're normal. They follow the natural laws. Okay, if you don't do that, you need to start to worry about him or her. All right, so the question is that you probably have learned, say, thermodynamics is for equilibrium, but is that really true? Okay, it's not, because when we talk about the first law, we never talk about it should be equilibrium or not. We just say the energy is conserved. This is the internal energy. If you put heat into it, you do the work, do the mass, then just energy increase. It doesn't say the system has to be equilibrium or not, right? Okay, but most of the time when you learn thermodynamics, this term is not there because they talk about a closed system. But we know that there's no system to close. Okay, it's very difficult to make system close. Okay, or maybe I should not say no, but it's very difficult. But however, when Gibbs derived the thermodynamics back in 1870s, that's for equilibrium only. But it's a change here, right? You change it from Q to S, from U to mu. Okay. So now during this process, Gibbs decided he was only interested in equilibrium. So he dropped that term. Okay, drop that term. All right, so if you put that term back, you get extra term here. So now you see this one Q is changed to S, and that we just take hydrostatic at work, and the U, that's internal energy, changed to mu I, and they have that other term here. What's that term? That's the second law of thermodynamics, entropy production. This is entropy production term. Looks like I need to do this one. Okay. So now what it means is that you put a Gibbs energy back to the form with the entropy reduction, you have the extra term here too. Okay. So now you see compare these two, right? So you drop this term, that means low entropy production in the system. That means it's equilibrium. Okay. So now you see you can connect them together now. So that means if we model Gibbs energy as a function of temperature, pressure, composition, and the internal degree of freedom, then the system can be, the free energy can be for non-equilibrium system. Okay. So what is psi is internal state variables, because we know that everything we see today is not at equilibrium. Okay, you can always go energy lower. Okay. But if we constrained in the system, we say, oh, now I see at this constraint, the system at equilibrium. That's why we've always constrained. Okay. All right. So now I hope by this one slide, I will convince you that thermodynamics is not equilibrium only. Okay. If you consider internal degree of freedom, like internal state variables. Okay. So now we go back to entropy, right? Because entropy production is about the second law. It's about how system evolves. Okay. So what have you learned? Or you learned? We learned together when we were in college, right? So we learned that ds equal to delta q divided by t. Well, so this one is one equation we learned. Then we learned that s equal to kb log omega. And that's probably the most thing we learned so far for entropy. However, we look at those two equations, right? And remember at the beginning, I mentioned that entropy is multi scale. So there's no multi scale here. So something's missing. So where is the multi scale in this equation? Oh, two equations here. Okay, so that's important. That means those two equations we learn have some limitations. So what are those limitations? Let's look into it. Okay. So to emphasize the multi-scale entropy, well, we wrote a paper a few years back, but recently, talk about the multi-scale entropy. So it means that you think about the scale, right? Let's do experiments. Okay. For example, we have like 140 some people here. So we have 140 configurations, right? Okay. Each person. So we have 140 of them. Then can rearrange them. We can see different configurations. So that's it. We call it configuration entropy. However, each of you has entropy, right? So I have to add the individual entropy here. So it's individual entropy times this is probability, because we talk about probability, and then probably we're configuring together, so we get a total entropy. But most time we talk about the configuration entropy only with KB log PK here. So it means that each person has a lot of degree of freedom inside, right? For example, depending on what you eat and what you age, you have a lot of degree of freedom inside. If you do that one, you combine them together. So this is the total entropy of the system, like today's meeting, would be individual entropy together, and our configuration entropy among 145 of us. And then each of us could have multi-scale inside ourselves, right? So we talk about each of us, we have configuration entropy inside, and each this configuration inside of us has entropy. So this is multi-scale. So now I get the appreciation of the multi-scale now, right? We have the scale of this conference. Then we have scale of individuals. The individual can break down even more scales. So it's until you break down the quantum level, right? So you can add all of them together. Okay. So then our conference today, it's constrained from outside. So we have a larger scale. With a larger scale, it's materials advantage, for example, right? Or beyond materials advantage is the department you have there. So it's a few systems outside of our symposium interacting with us. For example, our dean, your dean, he has left. He has to leave the meeting because he has other things to do, right? So that's a constraint. Okay, that means we had 148 before. Now we only have 147. Right? So you have constraint outside. So that's interaction. Okay, if you put them together, let's go back to the equation we had before. So ds equals dq divided by t. So what is the constraint of this equation? Well, that means you have entropy change due to heat, like the heat from sun to earth. That's how Earth survives, right? It's because of heat we get from sun. And then, however, you make some changes to it. We get meteorites, right? You know, the Earth not only get sun, get the heat of the sun, we also get meteorites. We get the impacts from meteorites. That brings entropy too. Okay, so that's the entropy for the meteorites, right? That mass. Okay, then the chemical potential is basically the energy of that meteorites minus the entropy of TS entropy of the meteorite. That gives the chemical potential of that meteorite. And of course, our Earth is not in equilibrium, so you can have something happening on Earth, right? So that means that that process, those internal processes, they are irreversible. You can never come back. So this irreversible internal process will produce entropy. So the entropy production, that's the second law. So the total entropy of our Earth consists of three parts: the heat we get, the mass we get, and our internal entropy production on Earth. Now, of course, on Earth there's so many things happening, right? The forest, the river, so many things happening. Okay, so it's a very complex system. But conceptually, you can divide it into three parts. Now, look at this one: KB log omega. Remember, this omega is kind of configurations you have at a scale. So this omega itself is scale dependent. It's at a specific scale we're talking about. Like the conference, like today's conference, we have the scale of individual person. That's our scale. So if we log KB log 143, let's give us entropy for today. Okay. So if we take this one, we means all the configurations have the same energy, the same statistical equivalent. Okay. For example, we talk about ideal mixing. That's xi log xi. That's mole fraction. You learned in your thermodynamic class. However, for non-equivalent configuration, we know that, right? 143 people will have different configuration, different probability. So if you do that about entropy, actually it should be KB, PJ, log PJ. PJ is the probability of each configuration. Okay. So now, think about scale. It has both space and time. It's not only space, it's time too. Okay. So that means that when we do measurements, we average over space and time. Okay. So spatial resolution, you have naked eye, optical, SEM, TM. That give you different spatial resolutions. Time resolution is even more important. X-ray has a time resolution, and the synchrotron has another time resolution. Okay. Then you use X-ray to absorption spectroscopy, you get different time resolution and spatial resolution. Okay, so it's very important. At each scale, you have the entropy, and together you get the mass entropy. Okay. So of course, we are not going to discuss all the details, but I want to give you a paper to read if you want to learn more. See how I think about thermodynamics and entropy and how it's applied to many applications. I wrote an overview paper last year at ACTMAT. Talk about the computational thermodynamics and its applications, including the basic fundamentals I mentioned in a few slides before. You talk about stability as typical thermodynamics. You talk about cross phenomena, Seebeck coefficient, and so forth. Talk about transport property, diffusivity, conductivity, and talk about the mechanical properties too. Because all those properties, they are not, some of them not at equilibrium, but they are related to energy. If it's energy, you can do thermodynamics, because thermodynamics is about energy and entropy, of course. All right, so to do that, we'll have tools. I also want to introduce that I had a book, as Rashid mentioned, published a few years ago by Cambridge University Press. And we talk about high-speed tools, right? We need better tools. We need always develop new tools to do the digitization. Okay, it's all open source we had. We got machine learning tools. We got the DFT tools. We got the data processing. I get the data and process them to develop databases. And then we also do workshops to educate the people to spread what we believe and our tools we develop. So again, we have YouTube for our Material Genome Foundation and also our YouTube channel. If you type in Material Genome Foundation on YouTube, you'll find our channel. All right, so now I finished my science talk. How about you, right? So I talk about so many interesting science. You say, okay, what should I do, right? What about you? Okay, now first I want to congratulate most of you to join the Materials Advantage. That's the first step. As the first step, after your in addition to learn knowledge, to get into this profession. Okay, Materials Advantage, as Rashid mentioned, it was formed by 4 societies, 4 of the leading material societies in the United States. Well, of them, of course, international now: American Ceramic Society, Association for Iron and Steel Technology, ASM International, and TMS. As you know, that the Materials Advantage now has over 75 chapters throughout the world. So you're one of them. Congratulations. So as you may know, that there are many societies, right? Some major ones in the United States is started in 1871. 1871, remember, 1871, it's the important time there, right? That's the Industrial Revolution. That's the Gibbs developed the foundation of thermodynamics. Okay. So that was the American Institute of Mining, Metallurgical, and Petroleum Engineers that formed their society. Okay, that's shortly after the Civil War in the United States. Civil War is one of the very important war in the United States. Actually, that's the last war we had on the land of the United States. And in 1984, this is a big society. About 100 years later, they separated into 4 of them because they're so different focus now. So then a ceramic society, because they're not from metals, right, not from mining, they started their own society in 1898. And the Electrochemical Society in 1902, ASM International is 1913. Now it's over 100 years, close to 110 years now. And then some other ones here. Okay, I highlight this the red ones. That's the 4 societies came together to form this Materials Advantage society for our undergrad students. So how about my connections with the society? As I mentioned, I grew up in China. I grew up in a tungsten mine. So they make tungsten. Tungsten is you dig the dirt from the ground, rocks from the ground, and make tungsten, right? That's the process. So you can think about this one. This is like a SME, right? Okay, mineral processing. Okay, that's mining here. That's one. So it's part of AME. And then when I go to college, when I went to college, I started process metallurgy. So that's about iron steel process. Okay. So when I went to my master's degree, I started the metallograph and heat treatment. That was ASM. I mean, in terms of the science and engineering. And then when I started my PhD, I did a physical metallurgy, that's TMS. So it's all related to my profession. Of course, when I become a profession, and I need to decide which society to join, right? As you can see that, this is the two societies have been involved for over more than 2 decades. So ASM International and TMS. So I've been members of both of them for over 20 years. I served on TMS board. I served as ASM president and board. So I really find it so enjoyable to communicate with people and to learn from other people, and at the same time contribute to the society, to the community. So, and one question you may want to ask, why are there so many associations in the United States, right? 1800, right? That's just a civil war just ended in the United States. There's a very interesting book by a French. He wrote the book in 1835. That's even before the Civil War, right? Okay. He came to the United States. He visited the United States for a short period of time, I think about a half year. Then he traveled in the United States. And then he decided to write a book. He realized that, he mentioned that the reason is because the American individualism. Okay? He said it's so much contrast to traditional hierarchies in Europe. You know, you have the royal family, you have this very, very rigid structure, right, in the United States. But in the US, it didn't exist. Everybody is on his own. So because everybody's on his own, you get trouble, right? So you feel so powerless. You feel so powerless. Because you're so isolated from the rest. It's lost. So then the people think, gee, in order to make our voice heard, we got to form some association to let other people know our interest, to let other people know what do we want for the society. Okay? Then they start forming associations. So a lot of associations in the United States, in my opinion, it's probably way more than anywhere else. But at least it reflects this book. Okay, so now that's actually very interesting, right? Very interesting. Talk about individualism. As I mentioned, I grew up in China. I got my bachelor and master's degree in China. I moved to Sweden. I got my PhD there. I stayed there 10 years, about 10 years. I have 2 boys. They were both born in Sweden. Then we moved to the United States. Now I've been here more than 30 years now. I came here in 95, not 30 years. Oh, yeah, more than 30 years now. And I enjoyed it very much here. Well, not 30 years, 20-some years, 25, 26 years, that's right. So it looks like this place I lived the longest in my life. So when I look this back, think about the hierarchies I mentioned. Again, as I mentioned, I like to use one word to describe each culture. So I put one word here. I think in the Asian culture, at least in China, where I lived, and it's a very strict hierarchy structure there. You're always looking upwards and see what the king tells you what to do. Okay. And in Europe, it is you look horizontally. You want to talk with your friend, talk with your colleagues, make sure we get a consensus and make decisions. Everybody agrees, and then we're moving forward. So reasoning there. Okay. But you know, in the United States, as I mentioned, as the French author mentioned, is that it's individualism, right? You look at it yourself. What can I do? How can I do the change in the world? And you probably remember what you probably heard what Steve Jobs mentioned. He said he wanted to make a dent in the universe. Okay, that's pretty bold statement, right? Make a dent in the universe. I think Apple did already, right? You probably think iPhone made a dent in the universe, I think. Well, of course, you can think about Elon Musk, right? Actually, dent in the universe. He's putting people now in. He wants people in the Mars, putting people on Mars. Okay. Of course, you think about Facebook, you think about Google, you think about Yahoo. So this is individualism really expand your thinking. People talk about thinking out of the box. I will put this one say thinking without a box. All right. So I want to congratulate to all of you, to MA students. You enroll in college and you study material science engineering. In the United States, that about 2.1 million out of 3.2 million high school students go to college. That's about 2/3 of it. Okay. And there's about 622,000 the full-time engineering undergrad students. That's about 7% of the population. And there are about 4,000 in material science in the United States. That's 3%, right? So it's a very small portion of people. Okay. And then even fewer people join the MA. Okay. So you join MA. So what does that mean? That means you are thinking about the future. You're thinking about what you want to do. You're thinking beyond the classrooms. So you're not constraining yourself by the classroom, by the knowledge you learn. You want to think what other people are thinking, right? How can I learn from my colleagues, my friends? Okay. How can I see my profession developers? So I really want to congratulate you for your thinking out of a classroom, like think out of the box, right? You think of a classroom as a box virtually. And you're also special because you want to do better than your best. Again, that's also my philosophy too. This is my president coin of ASM president coin, called "Do better than your best." That's the slogan I put on my coin. Okay. Again, I have a theory called the TKC theory. Is how can you do better than your best? Okay. Again, if you search TKC theory on YouTube, you'll find my recording there. Okay, so I give you one slide about TKC. We learn thermodynamics, kinetics, and crystallography. Thermodynamics give you driving force. Okay. So you decide to get driving force, you have to define your goal. Okay. You have to know what you are, where you are. You have to know where your goals will be, so you can evaluate driving force. And then you have to overcome the barrier because everything has a barrier, right? Nothing is easy. And also you see that the middle of the barrier is unstable. That means unstable give you frustrations, right? Give you challenges. Okay. You have to find the best path so you can lower the barrier. But in any case, you have to overcome the barrier. Okay. And then if you continue, you know the crystallography. Crystallography about interface, because you're going to interact with the people. We overcome the barrier. You can interact with yourself, of course, that's the first one. Then with your family, with your loved ones. Okay, there are a lot of constraints to you. So you have to be coherent with yourself, right? And coherent with your family, coherent with your friends. Okay? So if you're not coherent, you probably do some changes, right? Either change yourself or change other people. Okay? So you have to be flexible. Okay? Now, if you can do these three things, then you'll be very enjoyable. You enjoy what you do. So, all right. So, what do you like to do after you have the bachelor's degree? I know that many of you are going to graduate this year or next year. What do you like to do after your bachelor's degree? So that's just kind of a goal, right? A goal in the future is very difficult to predict. Extremely hard to predict the future. But you can look at what you have now, right? What you can do? Well, you can do two things, right? You can go to industry. Go study your business. Okay? And many people do that. Or even some people even did not finish college, right? To start business, like Mark Zuckerberg for his Facebook. So you look at the people graduated from bachelor degree, 2/3 of them go industry. Yeah, and many of them, some of them go MBA degree, and then about 1/3 goes to grad school because the people starting their own business is very few. So it's almost a zero fraction, so to speak. Okay? But 1/3 go to grad school. Okay? So that means, of course, there's a statistic, right? Because in your class here, because you go to MA, a chapter, maybe more people will go to grad school. Okay, but anyway, that's a general number. So now, how many students go to grad school go to different degree? Of course, now I don't have that number because the number is difficult to get, but I can look at my group. Okay, I have had 11 master's degree students in my group in the last 20 years. So about 4 of them went to industry, and the 0 go to national lab because national labs they want the PhD degree, and 7 went to PhD program. So now you see you get another percentage like more than 4%, right? About 4%. Okay, goes to 1, so it adds more to industry. Okay, and then I have had 29 PhD graduated, about 1/3. Little higher than 1/3 goes industry. So now add more to industry. There are 7 to national labs, 7 to university, and 2 still doing postdocs. So now when you see that, is what's the percentage? The overwhelming majority goes to industry. Okay, over 80% of the bachelor degree students go to industry. There's a movie called Industry movie. That's pretty interesting. I actually talk about the young people about their career. If you want to get that movie to watch, Industry. It's a very interesting movie. Okay, so now that means you need to decide why you're going to develop a profession, which society should you join. Okay? So of course, depends on what you're going in the future, right? Okay, now I give you one organization, one society. Is this society here? I'm not giving name yet. I'm giving name at the end. Maybe I give you if anybody wants to say what name is. So this society has 81% of the members are from academia. 10% for industry, 7% for government, and the rest are from the nonprofit and others. And it has 52% of members in the United States, have 30% of them are students. That's one society, one of the societies. And another society has 42, about half of this one in academia, increased 4 times about industry and the government and so forth. This one has 60% of people from the United States and 39 of the students. Then the third one is 80% from industry members and 20 from academia and 2 from the government. And 80% of members are in the United States and 15 are students. Okay, if anyone you want to guess what the 3 societies, you can unmute yourself and they talk about it. If you don't want, you can put in the chat. Okay, so I got 1, 2, 3. All right. So now you see this number is close to the number of how many bachelor students go to industry, right? 80%, right? I still have only 80% of people, 80% of bachelor degree students go to industry. So it looks like this one should match the bachelor students, right? So this one is probably more to the people going to universities as professors, right? This one is probably between, right? Or maybe it's national labs, right? You see, national labs you have now 14%, right? This is 2% here, government, and this is 7%. This is double. Okay, this is double. This is reduced by double. It's 4 times. This is double. Then come this one, right? So it's about between. So more like a national lab and academia combined together, and industry too. All right, so I leave this one for you. We answer this one at the end of the talk. I encourage you to put your comments in the chat. Okay, so I told ASM. ASM is headquarters. I've seen many societies, and this is the most magnificent structure for any professional societies. I'm not going to play the video. Maybe I should play it. Let me see if I can play it. I don't know whether you can see it or not. Oh, you probably cannot see the video.
We can only the sound. You can hear only the sound.
You can see the sound. Okay. Let me see if I can show the. In addition to this one, I can show this one too, I believe. Yeah, it looks like I cannot. But I say there's a link here. You can type the link and to watch the movie. Okay. So now I need to go back to that one. Okay, I'm going to close that video, but it's a magnificent video. Maybe I play this video at the end of my presentation. Okay, so ASM is a Materials Information Society. It has about 20,000 individual members. You talk about Swiss society, I mentioned it there before, we're the largest one. And the major value to members is the professional development, technical information about materials. And this is the other side of the present coin I have. Talk about this is the dome. It's a dome. I mentioned it. This is inside the dome. Very beautiful garden. Yeah. And its information is started from the beginning. I mentioned that ASM was established in 1913. The reason it started is because information. They found that the founders observed a growing need for the exchange of technical information about among the craftsmen and employees in 1900s. That's because it developed a new thing you can experience, you write down in the paper, right? Because they found that we need to exchange this information to preserve this information, okay? So then this William Hunt Eisenman, in 1990, he took over the leadership. There's 25 chapters, and then to put the document together, okay, and started to publish information, okay, publish information. So change the name to American Society for Metals, that's ASM, and it's all about information. Starting from 1921, first is about the steel treaters, right? Treaters, how you treat steel treatment, heat treatment. Then write the books, write the technical sheets. And the data sheets, that's 1920s, okay? And then handbooks, okay? That's 1940s, that's after the World War II. And now we have 38 volumes of the handbooks. Of course, we're going to digital, right? We're going to digital, okay? Now that's handbooks. Now digital means that you got to have a lot of digital contents. So a lot of information now is digital form. The digital handbooks, okay, online databases, journals is all digital now. So our goal is to put all information we have in the digital form. Okay, this is not the education. All the training courses are also online. It's a digital form now. So our strategy plan is that we want to continue to be the global resource for materials information. We want to gather, process, and disseminate materials information globally. We have three criteria. We need members, right? We need members. We need technical contents. We need partnerships. Okay. So MA is a great vehicle to build up this kind of connections. We want to digital first. We want to interdisciplinary. We want to reach the mechanical engineering, chemical engineering, and all the manufacturing people. We need a global network. Of course, we need diversity, right? Because when the world is flat now, basically, right? The world is flat. If you read that book, because the telecommunication makes everyone has the same playground. So the future is data ecosystem. Okay, we need to collect the data, process data, refine the data. We need a computer. We need the tools. We need digitization. That's really the digitization part. Okay, we are the member-based society. Okay, you join the Materials Advantage. You're part of the ASM family. You can also join chapters. I don't know whether we have chapter in your country. Maybe a Zq Liu knows that. And after the chapter, you can join the committees, technical committees. You can join the affiliate societies for different specific topics. And we organize events, we have publications, we do education, we develop partnerships. And after that, you can still join the board of trustees to chart the strategy of ASM. And of course, we need people to do that work because volunteers cannot do all of them. So we have many directors, we have the headquarters, we have departments, we have employees. ASM has like 70 employees at the headquarters. The Zq Liu is one of them. So you can get more involved. Well, you join the Materials Advantage, that's a very good first step. And you can also join Alpha Sigma. And you can join chapters. We have 68 chapters. Now I think it's more than 68 now, because we just have 2 created in India. So we probably have 70 now. We have in Canada, India, we have Europe, we have China, and Mexico. Looks like we don't have in Bangladesh. Why don't we form in Bangladesh for chapter 2? And then you can come to the Dome for the Leadership Day. And you can join the administrative and the technical committees about publications, about conferences. You can join the affiliate societies. Now we have 6 of them. Depends on your expertise. And then you can do the board of trustees. And as a student member, you can also join student member board of trustees. Every year, we select 3 new student members to join the board of trustees. So you can see, you can experience how the board works. Okay. Maybe you can decide, okay, maybe this is a place I should go in the future, right? So I encourage you to apply for this student membership and the board of trustees. They can join the task forces, you can join the nominees and nominee committees, they become the board members, and they continue for your career development. All right, keep asking questions. Why am I doing this, right? How can I do it better? Right, so I hope you can look at my TKC theory, give you some information. This is one of the leadership day we had on the Dome. Isn't it very beautiful? It's just marvelous. Okay, I mentioned about the benefits. For students, you have a lot of scholarships we offer. Okay, you have a lot of contests you can participate. You have a lot of conferences you can attend. As student board members, I mentioned, well, a lot of magazines published, or travel grants for that. Okay. All right. So I hope all the best to you for your study and your career. I hope to see you at the ASM events in the future. And also I will take the invitation from your dean. Next time I come to Asia, I will come to visit Bangladesh. I've never been there. I've traveled for more than, I don't know how many countries, 30, 40 countries. But Bangladesh was one place. I visited India 2 years ago for the first time. So Bangladesh could be the next one. With that, I want to thank you for your attention and I wish you all the best.
Thank you, Professor Liu, for your wonderful presentations about Introduction on Materials 4.0 and about what students can do in near future about the career. So I think we can understand the importance about not only about knowledge, also about knowledge sharing, knowledge disseminating using societies. So the students can participate, because most of the attendees here are undergraduate students. So after graduate, a large portion of them go to the United States for pursuing their higher degrees. So they may find them interesting. Also, the students who don't go abroad and join industries, like statistics show, you have shown here. So this happens also in Bangladesh. So whoever go to the universities, they can also participate in the society so that they can get knowledges about how to make processes better. Like we have lots of steel plants in Bangladesh, and also non-ferrous foundries and manufacturing plants. Nowadays, in Bangladesh, where Samsung has made local mobile manufacturing plants in Bangladesh. Also, some automobile vehicle manufacturers are moving in Bangladesh. So metallurgy has lots of scope in Bangladesh right now. So at the same time, so being part of societies will help them with getting and sharing technical knowledges. I firmly believe. So we have some questions in our chat box, and do you want to go through them right now, or you want to go back to them through email? I mean, which way you prefer? There are, I think, 5 or 7 questions.
Do you want me to answer the questions now, or you want to? What do you want to do?
I mean, if you can just give them a short, brief answer if you want. If you're available, I think.
Yeah, I could.
Yes, I think that's better. Do you want us to read this out to you, or you want to go?
No, I can share. Let me just. I can share the screen on the questions.
Yes. Okay.
And then you can see those questions there. Okay, let me see. How do I share that one now? I need to stop sharing first. That's right. Let me stop sharing first. Then can share that the question. Let me just share the question. Is this one here? That's right. No, I need to make it a separate one. Let's say pop out. That's right. Now I can share it. Share the pop out. Now I can just go through the questions.
I think I will try to share them. I'll try from my window.
Do you see my screen now?
Yes, yes, yes.
Okay, there's questions. Do you see the questions? Maybe not very
Not right now.
Either.
Not yet.
You see the chat question here?
No.
No, you don't. Okay, so let's just read the questions then. The questions from.
Yes.
Is that okay?
Yes, sure, sure.
Okay, so first question is that if an alloy's mechanical properties calculus with DFT method, there's not enough papers. We have one paper just to get published. If you check, not published yet, it's on the archive. If you look at my paper, 2020, I cited that paper on the mechanical property prediction for DFT. Of course, remember that is multi-scale. So DFT is one scale. So you have to get the crystal plasticity in the middle to predict the stress strain curve. The idea is that starting with DFT, you can predict the stress strain curve. Okay, that's a question on that one. Let's see. So the second one is that what is the core philosophy for validating computed or digitization based on prediction when type of experiments be conducted where simulation are different, right? Are different. Okay, so that's actually a very good point. The very important is because that simulation is always a simplified case. Okay? So you really need to put this different configuration together and to predict the reality. Most of the time you take one computation, you're going to one configuration or couple of configurations. So that's not enough. So you need multi configurations at different scales, put them together. So again, that's how we predicted the critical point. You know, critical point is the instability, right? By putting different configurations together, you can predict instability. Instability is the most difficult to predict because of singularity. So if you can predict a singularity without experiments, that means you understand the system. Okay? So you have to make sure you get all the configurations there. And then there's Sumayatu Asha has a question. I have faced a hard time with publishing research that is solely based on computational work. Okay, so the importance is that you have to make a very well-defined assumption in your configuration, in your computation. As I mentioned, computation is a part of the reality. It's not the full reality. So you should not directly compare with your computation with experiments. If you do that one, you don't agree. Okay, that means you should take different computations and put them together, then understand the reality. Or you can say the reality, the major contributing to the reality is this factor. Okay, so you can down select what's important. You can do different computations and figure out which one is more important. Okay, so that's what it do. So sometimes people have the expectation computation should predict the reality. No, it cannot, because reality is much more complex than their prediction. So you have to put a lot of configuration together. That's what entropy, as I mentioned, because entropy is multi-scale in terms of both space and time. Okay, so you have to put both together to really reproduce reality. Otherwise, you know that your prediction is away from the reality. Okay. All right, so the second question is from Abrarov. How can we be confident in coupling computations and modern studies with computation mechanical models in a consistent way? Since due to computation limitation, lots of internal approximations have to be made with each model to simplify computation. That's the exact question I just answered. Okay, so if you go back, for example, part diffusion, right? Diffusion. If you look at about 13 years ago, most of the diffusion coefficient was predicted by DFT calculation plus molecular dynamics. That's right, because kinetic process is moving, right? Thermodynamics has no time. So how can you connect these two weeks time without time together to predict the diffusion coefficient which is the kinetic properties. So we had a paper in 2008. So we did that. How do we do that? So we take all the possible configurations during the diffusion, calculate the energy, then put all this configuration into the statistical model, which developed by people before, called transition state theory, then can predict the diffusivity. That's just the example to show that, right? Okay. So again, it's very important. Your ultimate check or your simulation is the experiment. Okay. You can have a hypothesis simulation, but until it's proven, validated by experiment, it's still a hypothesis. But of course, we know that our hypothesis computation is not complete. So, however, if your computation captures the main features of that phenomenon, then your results can be compared with experiments. Before that, it's just the hypothesis you have. All right, so the next question by Reza Tahia. A lot of methodological design is based on empirical experimental studies, often driven by empirical equations formulated by lots of experiments. How valuable can computational contributions to the field of metallurgy as opposed to one explored field? That's a great point. So our knowledge before was accumulated by experiments. That's because we could not fully understand it. So our understanding is limited. That's why we do the microscopic observation, we draw some conclusion. What conclusion did we draw? We draw from the observation, we draw what we control, right? Then we say, oh, this is all connected. That's just like machine learning. That's how machine learning works. Actually, of course, our brain is a machine learning process, right? It's basically our brain takes what we observe, process it, and give us a model, right? Now, can we understand better of that one? So that's what computational comes into play. So computation can dissect it. So we don't really understand what's happening there, right? So now if we can understand what's happening there, we build our models, then we can predict the things we did not know before. So we predict that we do experiments. Well, the outcome of the experiment could be two things: agree with your prediction, or doesn't agree, or something between, right? So what does it mean? If it agrees, that's good. That means you capture most of the things in the reality. If it doesn't agree, that means you do not catch all the features in that reality. That means reality is more complex than you thought. It's more complex than your model can capture. What you do? Well, go back and refine your model. Just like you learn the experience, right? So you learn better model, and then you do next one. Okay, now if I can learn everything I have, now I can predict this one, that's fine. But then a new problem comes, right? They predict something, then you do the cycle. Of course, never ends, right? Never ends. All right. What are the initial steps to learn DFT? Okay, that's a very important question. Yeah, you don't have to fully master the quantum theory. That's what I think. Because just use the tool, right? You start with the tool first. Okay, just like you drive a car. You don't have to understand how the combustion engine works. No, you don't have. You drive it, right? So just like you can drive the machine for the DFT calculations. But of course, if you understand better, you need to get a theory and all the tools, right? So it's a different level. Again, it's multi-scale. It depends on your purpose. Okay, you can just first take a class, take a lesson to do how to do calculations, right? For example, how to calculate the nickel. We have a paper come out. Actually, we developed a high throughput tool called the DFT-TK. I mentioned that one. If you go to www, I put in here, dfttk.org, you can get our free code. But you have to have a VASP to run it. We have not defined the codes yet. Okay. So learn how to use it. Unless you are a physicist, you want to start from theory, that's fine too. But for most of our engineers, we want to solve a problem. So we take different tools, right? So you grab all the tools you can have, put them together, solve your problem. And if that tool becomes so important to you, you want to become expert at that one, then you can learn more theory behind it. I have not understood another question from Samit Bomik. I have not understood what this 3 pie chart on membership distribution is about. That just tells you how many members for industry, how many members from national labs, how many members from universities, percentage-wise. If it's first for thermodynamics, of course, if you ask me, that's my book, right? And I think in the community we have a problem. People separate equilibrium thermodynamics with irreversible thermodynamics. That's a problem. But I think they are connected together if you put that one term, as a d psi into the equation. There's two of the same equation. Now the only question is how you solve it. Of course, you can solve as we did before. You drop that term, you solve equilibrium, that's Gibbs did. Or you drop you take that term separately, solve the irreversible thermodynamic problem, transport problem, for example. But if I put them together, I solve both. And as far as I know, there are only 2 books in the literature talk about the 2 models. It's my book, and also the professor I learned from is Max Hillert. Okay, Max Hillert's book and my book talk about the integration of these 2. If you want to do that, if you search Hillert, you can find his book. Should our professional end goal, academic research, industry activity, we will into, if that factor, should we take into account of difference between the academic and industry, or too early to plan so far ahead? That's actually very interesting. It's a goal setting, right? As from Kaushik, Roy, Short, Harry, yeah, it's your goal setting. Of course, when at your age now, you don't know what you want to do, right? But however, how can you decide? How can you decide? Well, you have to decide now. You have to do some preliminary decisions. Are you do you really want to learn science, contribute to the scientific community, or you want to make something to contribute to the humanity? Of course, science ultimately benefits humanity too, right? At the end. So it's really what you want to do. Okay, really want to do. So that's very important for that. You have to decide, make that decision. And of course, you can change it. You can change it along the way. Okay. Okay, now material science, that's what I said. For example, I started with process methodology, I went to physics methodology, and then now I'm teaching thermodynamics mostly, right? Do I require advanced computer scale for programming? Well, you learn it, right? You learn it. You just learn, right? You see so many knowledge, you can learn all of them. So you have to learn what you want to do. Okay, then you become an expert. Then you work with other people. Okay, to help you to, for example, mechanical properties. I didn't work on mechanical properties, so I had a professor at Penn State work together. Now we do a lot of mechanical property prediction. Without that professor, I will not do that. Okay, how does ASM help students and young professionals outside the USA? Well, you have the MA, right? Material advantage. You can start with chapter. Then you get more involved. Okay, so it's really your initiative to build up your network and to build up your connections with other professionals. So you will become one of them. Then hopefully you can gradually enrich yourself and be better and better. What are our current computation limitations to study high entropy alloys? Well, high entropy is complex, right? But it's not that complex. Think about a nickel-based tube alloy. Nickel-based tube alloy has more than 10 elements. High entropy alloy, the 5 to 6 elements. It's less complex than the nickel-based tube alloy will have. So do we understand everything in nickel-based tube alloy? No, we don't. We start studying, right? Again, you're moving your computational close to the reality. Okay. If we can completely predict everything in the reality, well, that will take a very long time. What should an undergraduate focus on learning first? Machine learning or computational methods? Well, I think we should learn thermodynamics, kinetics, and crystallography first. That's the 3 building blocks for material science. Then you decide what to do. Machine learning is a tool. Computation methods are tools. Okay, they're all based on thermodynamics, kinetics, and crystallography. Okay, I think I answered all the questions now. Thank you.
Thank you, Professor Liu, for your wonderful answers and taking time to answer all the queries. And I think we and like about us, I mean, here the students most are from the material science and engineering. We call it here in materials and metallurgical engineering. So, and also we have some other students from other universities as well. So what I mean, usually in our second year, we study thermodynamics, and then in fourth year we have a year-long thesis for undergraduate students. So during that time, sometimes they use nowadays they're from last 1 or 2 years they're trying to use DFT. I think they use tools from GitHub. There are some tools on Python based on GitHub, and also sometimes we try to use some calculate methods. I mean, we don't understand all of it, like how actually calculate multi-component systems is working, but we use the tools like empty data, Geometry Pro, or Candid, try to do some calculations, precipitation kinetics, this kind of work we're trying to do nowadays. And so I think based on that, I think we are really, it was a very interesting presentation. And thank you for your patience for answering all the questions. and you have
I just like to interact with students. I like to work with students. I think because you are the future, right? You are the future.
Yes, and I think you have seen that. I mean, they're very much interested. I think, and if you give them time, they will ask more questions, because this is a new field. Like if you go for computational thermodynamics, this is the field. It's the booming field, and especially with the Calfed, and because of the new entropy alloys, high entropy alloys. So this is a booming field, and people are like to work on this field. And now with these Python tools at GitHub, so they're having fun. I think, especially when they go for abroad for the masters or PhD, then they learn how to use those skills more. And then sometimes, like tomorrow and day after tomorrow, we have sessions where they will know about how to use these tools. So this is a really helpful for them. And we have a few faculty members here, and I just want to tell everyone that when I asked Professor Liu about whether are you interested to give a talk, I mean, through Drew Fleming, he just left a few minutes ago, and he agreed spontaneously that okay, I will give a talk to the students, and it was really wonderful. And I whenever I emailed him, he just replied to me within a second, and he always helpful. Whatever I asked, he showed me his presentations, and whatever I asked, he said, okay, I will try to adapt. So this is, I really hope that we'll meet you in person someday. Actually, this is just my personal. Actually, in IMET, I have a presentation, but unfortunately, due to COVID-19 situation, I cannot go to IMET this year. So I'll do a virtual presentation this year. So I told Drew that maybe next year, if I go, then I will meet him. But now I'll obviously meet you, not only you, and your team as well, if I or any other faculty members or our students go abroad. And recently, I think we had a few students graduated from Penn State, completed the PhD from Penn State. And so we'll try to meet you. And also we'll try to, like our Dean, Professor Tamim said, we'll try, when the COVID situation is minimized or we feel better, then we'll try to invite you, so that because of that Material 4.0, this is a really nice idea. You are because in our country now we are our university school, I mean the government and university, they're trying to merge the IR 4.0 with the university goals, so to achieve some SDG goals. So this is what we are trying to do. So we can emphasize the Material 4.0 from our metallurgical engineering department to the university and to the government, so that we can pursue that. We are a big shareholder on this to achieving this SDG goal. So with this one, I would like to really thank you. And Professor Mahbub Hassan, are you?
I'm here, Dr. Rashid.
Yes. Yes, can you say some concluding remarks on behalf of I think also we have Professor Bozlur Rashid. Professor Bozlur Rashid has more than 30 years of experience in thermodynamics. He is our teachers of all our faculty members. So we say he is our man of thermodynamics. So he has written a book on thermodynamics, and we for last 30 years or maybe more than 30 years, around 30 years almost. So Professor Bozlur Rashid, he is teaching thermodynamics in our and metallurgical processes. So he was here. Probably, I think, Professor Badr Rashid. Sir, are you here? I think.
Yes, I'm here.
Because you both have quite close fields, you want to say something. He's a senior most professor, Professor Badr Rashid. So he is our teacher of thermodynamics. Sir.
Okay, thank you very much, Rashid, distinguished guest. Many thanks for your lectures. I was very interested in your lectures because nowadays students don't often correlate thermodynamics with other subjects. They thought, what's the use of thermodynamics? I'm going to make steel or produce aluminum alloys, for example. What's the connection with thermodynamics? And they often feared about the subjects. So it's a challenge to teach them thermodynamics, and hopefully nowadays you lectures, and when they go abroad to study higher studies in materials science and engineering, they become aware of the importance of thermodynamics. And then it makes my life a little bit easier when they tell me that okay, your subject is important nowadays. Please, okay. So thank you very much again for your wonderful lectures. I hope all the students of material science and engineering will be able to understand a little bit about thermodynamics and their importance, particularly in this coming era, industrial revolutions, materials for IR4 and so on. So again, I thank you very much. So sign you over to Rashid.
Thank you. Thank you very much.
Thank you.
Okay, thank you, Professor Badr Rashid, for your inspirational talk. And now I'd like to request our head of the department, Professor Mahbub Hassan, to say a few words on behalf of the department.
Yeah,
and
thank
our
you. Actually,
students.
I'd like to say my thanks to Dr. Liu for his nice presentation. Actually, I had the whole presentation. It's very nice. Okay. And I think all the students, they also enjoyed very much. And they will be very fruitful for everybody. And, you know, in introduction, I did not say anything actually, but our Professor Tani, our dean, he already invited you. So I'm also inviting you to visit Bangladesh when you are free. Okay, it will be it will be very nice for us as well if you visit us in Buet in Bangladesh. Thank you again, Dr. Lee. Thank you.
Thank you for the invitation. I will come to Bangladesh, that's for sure.
Yeah, you are most welcome. Thank you, Rashid.
Okay, thank you, Professor Mahbub Hassan, head of our department. And with this one, I'm going to close our session and this keynote session. And any last words from Professor Liu to the students? Do you want to say something? Just
okay. First, I want to thank you for the opportunity to present here. I want to thank the students for attending my presentation. And the last thing I want to tell students that there will be a lot of challenges along the way because everything has a barrier based on thermodynamics. Everything you do, the universe is against you because you are producing entropy. So you have to realize that. So nothing is easy. It's going to be harder. If your goal is higher, it's harder. Okay. But don't be afraid of that. If you keep on working on it, you'll reach your goal. But please be flexible. And sometimes you have to modify your goals. And if you do that one, you will be successful. Wish you all the best.
Thank you, Professor Liu. And you are always welcome to our department, to our university. And sometimes we may ask you for more presentations on thermodynamics. So this is a topic of our, for some of us or many of us, we prefer thermodynamics because using thermodynamics, we can do lots of things. And especially we have to learn math as well at the same time. So we can use the tools and math, then we can do lots of things using thermodynamics. So now we're closing our session now. Thank you very much, Professor Liu, and thank you all our faculty members from the department, from outside the department. I've seen a few faculty members from other departments, mechanical engineering department, naval architecture department, have joined us, and also from our dean was from petroleum engineering and chemical engineering department. So we have students from our department and some other departments from outside our universities. Thank you all for attending, and thank you for your patience. I know it's a difficult time during this COVID-19 situations, even though you have managed time to join our program. Thank you all, and a special thanks to our special guest and our chief guest. Thank you very much, Professor Lee. Thank you very much.
Thank you.
Well,
have a good day.
Good
night, Leonard. Sorry, good night.
Thank you. You have a nice day.
Okay. Bye.
Bye.
Sir, I'm ending the live now.
Okay, you can close the live now, and our audience, you can leave our session. Thank you very much. We have a session tomorrow again at 7:30. We are using the same link, so you can join us tomorrow. Upgrade, is it at 7:30 or 7? 7:30, I guess.
7:30.
7:30.
So we'll see you at 7:30 tomorrow. So that tomorrow is different. So how to build career in Bangladesh, and what about our female students, female employee? I mean, female graduates are thinking about the career in MME. So we will. I think it will be different things we'll learn from these two sessions tomorrow. Thank you all. Thank you, sir.